errors and without errors. Okay. Problem number 1. Suppose node A sends frames to node B using sliding window protocol. So it just says sliding window protocol. Nothing is stated about the errors. So you can assume there are no errors. Assume that the size of the window is 7. So W is 7. And the sequence number of frames ranges from 0 to 7. That is frame 0 through frame 7. Further assume that there are no errors in the communication. And we define 4 sets, SA, WA, then RB and WB. So what is the meaning of this set? It's a slightly different notation. Okay? So look at this. If you can recall the lecture notes, we used to have a window. This is the current window, right? And inside we used to write some numbers. Do you remember? So these are, okay, so here I used a set notation. W is, A is the set of frame or frame numbers which could probably be sent in future without even waiting for the acknowledgement. That is, sender is permitted to send these frames. And between this vertical bar and the window, we usually have some numbers here. Okay. So the frame numbers, right? These are the set of frames which are outstanding. These are the outstanding frames. So meaning that they were sent, but the acknowledgements were not yet received. So we call them as the outstanding frames. Similarly, on the receiver side, WB is the set of frames with sequence numbers, okay, which this receiver is expecting to receive or it will receive in future. Okay? And RB is the set of frames which were received and put in the buffer locally, but the acknowledgements not yet sent. Not yet sent. Outstanding means acknowledgement not yet received. Okay? So if you can easily correlate the figure and the set notation here. Now we are given, okay, the initial state of the window on the sender and the receiver. Our sender S, receiver R. So sender side, okay, this SA is empty, nothing has been sent. So window contains 7 frames because window size is 7, 0, 1, 2, 3, 4, 5, 6. That means this WA, inside this window, you have 0, 1, 2, 3, 4, 5, 6. So meaning that the sender is permitted to send frame 0, 1, 2, 3, 4, 5, or 6 without waiting for an acknowledgement. Doesn't need to wait for an acknowledgement. Of course, if it gets an acknowledgement, it will expand, but there's no need to wait for the acknowledgement to transmit these frames. Okay. Similarly, on the receiver side, initially RB is empty because it has not received anything, and the window contains 0, 1, 2, 3, 4, 5, 6. These are the frame with sequence numbers 0 through 6, which could possibly be received. Okay, it's expecting those frames. Now the question is this: at time T1, node A has transmitted frame number 1. Note that the sender will transmit the frames only in sequence. So it says A has transmitted frame 1 at time T1, meaning that at time T1, these 2 frames have been transmitted, 0 and 1. Okay? So 0 and 1 are the outstanding frames now, and the window size will be shrink to 5. So it has now 2, 3, 4, 5, 6 because 0, 1 will be moved here. So 0, 1 will be moved here. That's what it means. So at different time instance, some events occur and you are asked to complete the table. So this is the table given. You can see there are some empty boxes, right? Some boxes are shaded. So you are asked to fill in these empty boxes. So for T1, just now we finished, we completed this. Now T2, there's another event occurs. Node A has transmitted frame number 4. Node A has transmitted frame number 4 means these 3 frames were transmitted. So this 2, 3, 4 will be moved here. and the window will shrink to 2. Window size is 2 now. It has only 5 and 6. At time T3, node B received frame 3. That means at time T3, okay, this has been shaded out, so let's not worry about the state at the sender. At the receiver side, it has received 3. That means it has received 0, 1, 2, 3. Now, this set of frames for which are buffered, for which acknowledgement not yet sent would be this 0, 1, 2, 3, and 4, 5, 6 will be the window, current window at the sender. At T4, node B has transmitted an acknowledgement frame RR4. So at T4, it has transmitted an acknowledgement frame RR4. RR4 means what? Receiver is ready to receive frame 4 onwards. That means receiver is acknowledging all the frames prior to 4, 3, 2, 1, everything. So as per this state, it is acknowledging 3, 2, 1, 0 because these are the frames which were received and kept in the buffer. So when you say RR4, these 4 were acknowledged. So this set becomes empty. Because this is a cumulative acknowledgement acknowledging 4 frames, this will expand by 4. Note that this 4 does not mean that it is acknowledging 4 frames. This 4 means that it is ready to receive from frame number 4. So it so happens that in this case, we have 4 frames here. T5, node A transmitted frame number 6. That means these 5 and 6 were transmitted. Now the window becomes empty. At T6, 2 events happen as per the problem. Node A has received RR4. Node B has received frame number 5. When node B received frame number 5, that means these are the frames which are received. So these 2, 4, 5 will be moved here. So the remaining is 6, 7, 0, 1, 2. And node A received RR4. So at this time, RR4 is received. That means the receiver is ready to receive from 4. The receiver is acknowledging the previous frames, 3, 2, and all. That means the receiver is acknowledging these frames. So this outstanding frames will be now 4, 5, 6. Okay. It is because 4 frames are acknowledged, this will expand by 4. When it expands by 4, the next sequence number is 7, because this is 6, then 7, 0, 1, 2. Any doubt? And you need to note one thing, window size, the maximum window size is 7. So at any time, the cardinality or the sum of the cardinality of the 2 sets would be 7. So here the cardinality or the size, number of elements is 0. Here it is 7, there are 7 elements, correct? So here 2, 5, 2 plus 5, 7, 5 plus 2, 7, 7 plus 0, 7, 3 plus 4, 7. Similarly here, 0 plus 7, 7, 4 plus 3, 0 plus 7, 2 plus 5, 7. If you don't get it in the test exam, that means something is wrong. Definitely your answer is wrong, right? Because the total should be 7. The number of frames, outstanding frames, plus the number of frames permitted to send should be W, that is 7. Similarly, for the receiver, the number of frames received, which are in the buffer, plus the number of frames which is permitted to receive, that should be 7. Any doubt? Yes? Problem number 2, give an example to illustrate the difference between flow control and congestion control. I think in the beginning of the lecture, when we talked about flow control, I already highlighted or emphasized the difference between the flow control and congestion control. So let's again recall it. Flow control is the problem between 2 people, sender and receiver. No one else is involved. Okay, it involves only two systems, sender and the receiver. Okay, switches, routers, link capacities, they don't have any role. They don't have any role here. Okay, it's the problem between sender and receiver. So that means we need to make sure that the sender is not overwhelming or jamming the receiver. Okay, sender should not send at fast rate. Okay, not to jam the receiver. That is the flow control solution which we are looking at. Am I correct? So that means what? Network might have huge bandwidth. Network might have huge bandwidth. That doesn't mean that there's no flow control issue. The network may have bandwidth. Whatever sender is sent, it should be able to carry it to the other side. But the bottleneck is the receiver. If the receiver is slow in processing the packets, frames or whatever it is, then there's a flow control problem. Okay. Just a simple example, if the sender produces 10,000 packets per second, sending to the receiver, whether the receiver is able to consume or process 10,000 packets per second. Okay? 10,000 packets will go through the network, may. Is that okay? Clear or not? So the problems are different. But sometimes the solution will help both congestion and flow control. Because once you reduce the sending rate at the sender, so obviously the amount of packets or bits or load you are throwing into the network is also small. Okay, okay, now what is congestion control? Congestion control, firmly defined, we need to make sure that the network is able to carry the offered load, offered traffic. Okay? So this is a network. I mean, maybe I just show you a simplified network. Okay? Let's say you take, let's say this is a router or switch, so packet switch or it could be Ethernet switch or IP router or anything. So, or let's say it's a router, okay, network. So different amount of traffic is carried between the nodes, right? So this node, let's say this is 1, 2, 3, 4, 5, 6. Node 1 may be sending data to 6, 1 to 3, 1 to 4, 1 to 5. So everybody is sending data. So they need not be the source. Maybe there could be other LAN or something. So the traffic from here enters here and they may want to leave through 6, right? So there are many sources which pump data or load, traffic load onto the network. Now you take any one router, let's say, so some packets or some data or some packets want to leave through this link, correct? So let's say it receives some packets from here, some packets from here, and they want to leave through this. Of course, the packets which are received from here, they may want to leave through this also. But just an example, we consider only one case. So the router has 3 links. The packets from these 2 links, they want to leave through this output link. So just a simple example, let's say the rate is R1 bits per second. This is R2 bits per second. So R1 bits are received here per second, R2 bits are received here per second. If the data rate at the output link is less than R1 plus R2, then there will be excess bits data, right? So, and that would be buffered locally. And if the buffer overflows, that's the strength of congestion. So basically, you want to see whether the network is able to carry all the traffic. Okay? So just again, there are many sources. This could be one source, this could be another source, another source. So data from multiple sources are sent through the network, whether the network is able to carry it or not. Is that okay? So now, let's say there's a flow from, let's say, 1 to 6. Let's say 100 Mbps load is flowing from 1 to 6, 1, 2, then 6, right? So that means it will use up 100 Mbps here, and it will use up 100 Mbps on the next link also. That means it will add a load of 100 Mbps on the first link. It will add load of 100 Mbps on the second link as well, right? This is something like 100 passengers are taking flights from city 1 to city 6. So they all transit through 2. So this is the first flight. Link 1 to 2 is the first flight. So you need to reserve 100 seats for them, right? And second flight, 2 to 6. Another flight, again you need to reserve 100 seats for them. Is that okay? So this load will use up bandwidth on every link. That means this load is the offered traffic load that will add to every link. Is that okay? So now let's look at an example to better illustrate the difference between flow control and congestion control. Let's consider a fiber optic network, okay, which has a huge capacity of 1000 Gbps. I mean, it's a total capacity, not just one link capacity. Okay, there are many fibers. Each fiber operates maybe 1 Gbps or 10 Gbps or 40 Gbps. So the total capacity is, let's say, it's huge capacity is available. Now, a supercomputer is trying to transfer a file to personal computer. So supercomputer, okay, is generating data and it is sending data. Okay? So it is trying to send at the rate of 1 Gbps. Okay? So for this data to reach the destination, we need just 1 Gbps bandwidth on every link, right? Because it's a fiber optic network, huge bandwidth is available as per the problem statement. Bandwidth is not a problem. The data packets, all packets will reach the other side. But the supercomputer is trying to send to a poor personal computer. It's not fast enough. The processor and other things not fast enough compared to supercomputer. Okay, so the personal computer may not be able to process all the data which is sent by the supercomputer. So we say that flow control is required because the personal computer should be given a chance to breathe. That means it should be able to process, that it should have enough processing capacity to process all these packets within a second, whatever is received. Is that okay? So this is a flow control issue. Now look at an example where there is no flow control problem, but there's a congestion problem. So here there's no flow control issue, but congestion, there's a problem, there's a congestion here. Okay? So we assume that there are 1000 computers. They are all with equal capacity, equal processing capacity. 1000 large computers, that means more or less same capacity, okay, equally powerful. And 500 computers, let's say C1 to C500, just without loss of generality, we assume that 500 computers are trying to send flows to the remaining 500 computers. Okay? So let's say C1 is sending traffic, which we call it as traffic flow, okay, which will go through multiple links. C2 is sending to C502. Let's say C500 is sending data to C1000, computer 1000. Okay? So there are 500 traffic flows. There are 500 traffic flows. Assume that, so this data or traffic, okay, travels through a network, okay, store and forward network, okay, maybe switch based or router based, but the link capacity is only 1 Mbps. Link capacity is 1 Mbps, okay, and each computer is transmitting, each computer is transmitting at the rate of 100 kbps. This is only 100 kbps. This is only 100 kbps. Because all these computers are equally capable, performance-wise, right? Receiving 100 kilobits per second data is not an issue. There is no flow control problem. There's no flow control problem. Whatever C1 sends, C501 should be able to process it. Correct? But now there can be congestion issue here. Maybe let's consider a specific example. These numbers are given in the book, but I have chosen these numbers. Okay. Assume that there are 50 links in the network. There are 50 links in the network. Something like 50 flights are operating between few countries, let's say. Okay. And each traffic traverses 4 links. That means each person takes 4 flights, maybe a domestic flight, international flights, another domestic flight, something like that. Okay. Assume that each traffic flow traverses 4 links before reaching C501. So this is link 1, link 2, link 3, and link 4. This is our assumption. Okay. That means each traffic flow load is only 100 kbps, but it adds 100 kbps load on each of the 4 links. Right? 100 passengers, they want to fly from C1 to C501. Each of them takes 4 flights. So transit. Okay, they need to transit through multiple cities. Okay, so each flight should have the capacity to take these 100 people, passengers. Correct? So the total load which are sent through the network is 500. There are 500 traffic flows. Each traffic flow load is 100 kbps, and each adds load to 4 links, because we assume that is traversing 4 links. Assume that we use a very perfect routing algorithm, that these links, okay, or these flows are uniformly distributed on the different links. Because there are only 50 links, 500 traffic flows, and each traffic flow traverses 4 links. So we need 2000 links, right? But there are only 50 links. That means same link is traversed by more than one flow. Is that okay? So if you assume that perfect load balanced routing, then the load on each link would be just divided by 50. So this is the total load divided by 50, that gives the load on a link. So the minimum load, at least there should be at least one link where the load should be 4 Mbps. Okay. Because our assumption was that the link capacity is 1 Mbps, now the offered load is 4 Mbps. That means it can transmit only 1 million bits per second, but the load is 4 million bits per second, so it's not able to cope up. Every second, 3 million extra bits arrive. So if it continues, the buffer will grow. It will lead to congestion. So this example shows that there is no flow control issue, but there's a problem of congestion. Is that okay? But maybe later when you study TCP and other things, the solution wise, okay, so if you ask the sender to reduce the speed, let's say for flow control purpose or congestion control purpose, that will directly or indirectly will help to solve these two problems. But the problems are different, right? If the sender slows down, let's say supercomputer slows down because of flow control issue, obviously the load pumped onto the network will also be lower, right? Problem number 3, describe a scenario to illustrate the need for limiting the window or maximum window size to 2 raised to the power k for a k-bit frame sequence number with go back n IRQ. I think this several examples we have been using, right? I was using frame numbers, frame 0 to 7. That means k equal to 3. We use 3-bit sequence number, 0000 to 111. Is that fine? But W, we are not using 8. W cannot be equal to 8. So W should be less than or equal to 7. That's what it says. Why is it so? Anyway, we are not looking at the formal proof, okay, but we give sometimes to prove this is correct when difficult, okay. To prove that is wrong, easy, okay. You give just one counter example, you can prove that it is wrong, right? So let's say I make a statement. If you want to dispute, you want to prove that what the statement which I made is wrong, you can just give one counter example, right? Prof, look at this case. No, your statement is not true, false, right? So it's not a very formal proof, but though I take some specific example, okay, this helps you. I mean, it's a kind of proof also, help you better understand why it should be. Let's consider k equal to 3, because this is what we have been considering, many examples. Assume that frames are numbered from 0 through 7. W, let's say we use window size W equal to 8. What happens? Is it a problem? That's what we are going to check. Okay? So W equal to 8 means at any time there can be 8 outstanding frames. That means sender is permitted to send up to 8 frames without even waiting for the acknowledgement, correct? That means number of outstanding frames can be 8. Now look at this situation. Sender sends 8 frames 0 through 7. So it sends frames 0 to frame 7. I'm not showing each frame individually. So frame 0, 1, 2, 3, 7 are sent. We assume that W equal to 8. And later we see that that would lead to, okay, the case which is not possible. Okay, this leads to some false or not possible case. Then we say our original assumption is wrong. Okay? We assume piggybacked acknowledgement. Do you remember piggybacked acknowledgement means the receiver is sending some data frame. So it's not a separate acknowledgement frame, but along with the data frame, it is sending the acknowledgement. So it's a piggybacked acknowledgement. So the acknowledgement which it will send will be RR0. RR0 means it's acknowledging, it's ready to receive 0 onwards. That means it's acknowledging 7, 6, 1, all the previous frames, correct? Let's say the sender sends another batch of 8 frames. Window size is 8, it sends 0, 1, 2, 3, 4, 5, 6, 7. No acknowledgement received. So, but let's say after some time it receives RR0. Okay? Now there is a confusion. What is the confusion here? Assume that the second batch is all successful. First batch is successful, it received RR0. Second batch of 8 frames also successful, now it receives RR0. That's fine. That means this RR0 acknowledges the second batch. Now look at the case. The first batch was successful and the second batch all failed. There was a heavy fault or noise, okay? All 8 frames were lost. All 8 frames were lost. Even in that case also, after some time, the receiver, because it uses piggybacked acknowledgement, whenever it sends a data frame, it will repeat the previous acknowledgement. It will repeat the previous acknowledgement. So it will tell, hi, sender, I am waiting for 0. Okay? So in both cases, the receiver will send RR0. When the receiver receives the second batch, it will send RR0. Okay? When the receiver does not receive all the frames in the second batch, in that case also it will send RR0 because it's waiting for 0. Correct? So when the sender receives RR0, it gets confused whether this RR0 is the acknowledgement for the first batch or the second batch. First batch or second batch. Correct? In both cases, RR0 will be received. So this should not be. So we restrict the window size to less than 8, 7, 6, 5 or anything. But if you look at, if you have window size 7, this tough situation will not occur. Right? Suppose window is 7, then this will first send F0 to F6, right? Then it will send RR7. then it will send F7 to F5, right? It will send RR6. So if the center receives RR6, that means both were successful. If the center receives RR7, that means the receiver is acknowledging the previous one, not this one, right? So this kind of situation will not arise. Problem number 4. Node A transmits 1000 byte frames to node B using selective repeat ARQ with window size window size 3 over 10 Mbps link. The link is 200 km long. Frame error probability is given 0.1. Propagation delay on the link is given 5 microsecond per kilometer. That means the bit traverses 1 kilometer in 5 microsecond time. Calculate link utilization. So just you can mechanically apply the formula. Window size is 3. Window size is 3. First step is you should compare 1 plus 2a. You should calculate 1 plus 2a. So a is TP by TF. TF is the size divided by data rate, 0.8. TP is the propagation time. 1 kilometer, 5 microsecond, 200 kilometer, it is 1 millisecond. So A is 1.25. So 1 plus 2A is 3.5. But W is 3. W is 3. So that means W is less than 1 plus 2A. The utilization will be W by 1 plus 2A. If W is greater than or equal to 1 plus 2A, utilization will be 1. Right? So because it comes under this, just W by 1 plus 2A, because the error probability is given, you have to multiply it by success probability. So success probability is 0.5 because the error probability is 0.1. So 0.77 is the utilization. Any doubt? Problem number 5. It's also same problem, only small difference. Maybe I could have merged these two into one problem. That's fine. As before, node A transmits 1000 byte frames to B. Selective repeat ARQ is used. Window size is 3. Link capacity is 10 Mbps. Link length is 200 km. Propagation delay is given. Calculate link utilization. And another interesting question, how many frames are sent in 1 second? So in the previous case, error probability is given. Now error probability is not given. So as usual, first you need to find 1 plus 2a. A TP by TF. 1 plus 2a is 3.5. W is 3. So W is smaller. So W is less than 1 plus 2a. So that means this implies utilization will be W divided by 1 plus 2a. So this is the utilization, 0.857. Earlier the utilization was smaller, 0.77, because there was some error. Now next question is, you need to calculate the number of frames sent per second. It's not utilization. Okay? So again you draw the timing diagram. So W frames are sent here, right? For every TF plus 2 TP, W frames are sent, correct? So this is TF, TF, TF. So to derive the utilization, we said that W frames are sent. So the useful frame transmission is WTF over TF plus 2 TP. That's equal to W by 1 plus 2A. That's how we derived utilization, right? Now we are interested to calculate number of frames sent per second. Same approach, same diagram. Instead of saying W frames are sent over, WTF divided by this, we say that W frames are sent for every TF plus 2 TP. It's a number. It is not the useful transmission time. So here utilization, useful transmission time is W times TF. But here we are interested in number of frames, not the frame transmission time. So we say that for every TA plus 2 TP, W frames are sent. So it is W divided by TA plus 2 TP. So TF plus 2 TP you have to express in second. If it is in millisecond, you have to use 10 power minus 3. Right? So you get 1071. Any doubt? So if you take stop and wait, the same argument. So stop and wait. Okay, so for every frame transmission, there's a wait of an acknowledgement, right? So this is TF, 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 TF. So for stop and wait, we say that, so this is TF plus 2 TP. So for stop and wait, we say that there is one frame transmitted. The useful transmission time is TF for every TA plus 2 TP, that's equal to 1 by 1 plus 2A. That's how we derived expression for stop and wait, right? So if we are asked to calculate how many frames are sent per second, not the utilization. Okay? Same thing, same diagram. So number of frames per second equal to, you argue now the other way. One frame is sent for every TF plus 2 TP time. For utilization, we say useful transmission is TF for every TF plus 2 TP. To find out the number of frames sent per second or per unit time, so you need to look at it from a different perspective. You need to argue that one frame is sent for every TF plus 2 TP. Right? So this problem is about this. So it's given the length, data rate, size of the data, and you are asked to find how many frames are sent per second. Frame transmission time, size divided by data rate, 400 microsecond. Propagation time is 500 microsecond. So 1 divided by TA plus 2 TP is 714. Okay? So now let me ask one question. Suppose you go back to this problem. Suppose W is greater than or equal to 1 plus 2A. We know utilization is 1, correct? But how about the number of frames? Number of frames per second. If W is less than 1 plus 2A, we say W frames are sent for every TA plus 2 TP time, right? If W is greater than or equal to 1 plus 2A, utilization is 1, right? So the transmission will be something like this. Window will never become empty, right? There will be continuous flow of frames. So you can easily find out how many frames are sent in 1 second. I leave it to you, it's not difficult, right? Any doubt? The last question, problem number 7. It's a bit more complex, but more interesting question. Node A sends 1000 bit frames. So if you look at the tutorial problem, some problems were taken from past year questions, even though I don't tell, okay, this question is from this exam paper and all, right? Okay. But this, I think, this exam paper was released 2001, 2 or 3. I think 2002, if I'm not wrong. Node A transmits 1000 bit frames to node C through node B. So now there are two links, A, B, B, C. So A is sending some data to C. So it sends data to B through one link and B to C another link. Okay. And some parameter values are given. The frame size is 1000 bit. Length is 4000 kilometer. The first link is 4000 kilometer long. The second link is 1000 kilometer long. And also there is error probability 0.1 for the first link, 0.2 for the second link. It's only for calculation purpose. In practice, error probability will not be very high, like 0.1, 0.2 and all. It could be very small, 0.00 something, okay? So let's not worry about it. Propagation delay is 5 microsecond per kilometer. This is a standard one. Between AB, selective reject ARQ is used. Sliding window is used on AB. But between B and C, stop and wait is used. Right? That means if you use selective reject basis sliding window ARQ, on AB you should be able to send more frames per second than what B can send to C, right? Because on BC, stop and wait. Because stop and wait means for every frame it has to wait for the acknowledgement. So if you calculate the number of frames sent in unit time in 1 second, okay, the number of frames sent on AB per unit time will be much larger compared to the number of frames sent on BC, right? Because this uses sliding window, this uses stop and wait. So as a result, what will happen? So many frames are sent per second here, but B will not be able to send this many frames to C in 1 second, correct? Is that okay? So of course there will be some buffer here, but if you want to avoid the overflow of the buffer, what we would expect is the number of frames which enter B on an average per second, okay, would be same or smaller than the number of frames that can be sent on the second link, right? You don't want too many frames on the first link, okay? You should be able to transmit more frames per second on the second link compared to the first link. So how is it possible? Because it uses sliding window, first one, second one is stop and wait. First set is not possible if the data rate is the same. One possible way is we can have higher bandwidth here. So that way we can try, maybe may not be guaranteed all the time, so we can try to send more frames per second. And it's given that A is sending at the data rate of 100 kbps. First question, how many frames are sent or transferred by node A on link AB in 1 second? So when we say how many frames, you should not count the retransmitted frames, okay? You should not count the retransmitted frames. That's why bracket I put original. Even if I don't put original, how many are sent? Because as far as the user is concerned, he is sending 1,000 packets, that's all, right? Because of the protocol or network error or something, instead of 100, we may end up with sending 105. But from the user perspective, it is 100 packets, right? So how many frames are sent in 1 second on the first link? Then calculate the link utilization on the first link. The third one is more interesting part. Determine the minimum transmission rate required by B so that buffers of B are not flooded. Okay? Because we want to have a different transmission rate, data rate or bandwidth for the second link, higher bandwidth, so that it should be able to cope up with the incoming data. So that's given as the hint. In order not to flood the buffers of B, average number of frames entering and leaving must be the same. Okay? Is that okay? Then there will not be any issue. So all these notations, TF1, TF2, TF1 frame transmission time on the link 1. So this suffix is number 1, 2, they represent the link number. Okay? So I think we have seen similar problem. Let's go into the solution straight away. For A, part A, first you need to find 1 plus 2A because it uses sliding window, right? So what is A? TP by TF. TP1 by TF1 means for the first link, that is 2. So you can use calculator to actually find out, okay? So 1 plus 2A is 5, but W is 3. W is 3. I think it's given. Window size 3 is used. But 1 plus 2A is 5. So that means W is less than 1 plus 2A. If W is less than 1 plus 2A, number of frames sent would be W frames are sent per TA plus 2 TP. TF1 to TP1, okay? Because there's an error, you need to multiply it by the success probability. W is 3, then TF plus 2TP, you have to find it's 50 milliseconds. I multiply by 1000 because I'm converting it to second. So I don't want to spend too much time on this. Then for the second part, find the utilization. Utilization is W divided by 1 plus 2A. Because there's an error, multiply it by 1 minus P1, that is success probability. So you get 0.54. Now the interesting part is the third one. So third one, okay, on first link, node A transmits W frames per TF plus 2TP time because it uses sliding window. On the second link, that is from node B to C, 1 frame is sent for every TF plus 2TP time, correct? So we want to relate these two. What we want is the number of frames transmitted by A per second should be less than or equal to the number of frames that could be sent out on the second link. So W by TF plus 2TP is the number of frames sent on the first link. That is number of frames received on the first link. Both are same, okay? And 1 by TF plus 2TP is the number of frames sent on the second link. So it should be the first quantity or expression should be less than or equal to the second expression, right? Now, you know W, you know TF1, you know TP1, you know P2, you know TP2, everything is given. What is not given is the data rate. So TF2, you can, from these expressions or inequality, you can find TP2, TF2, because all other values are known, right? So some work for you. So try, you'll get TF2 is less than or equal to 4.815. So TF2 is less than or equal to 4.815. We know that the transmission time is size divided by bandwidth. So this implies if this is equal to this, then we can say bandwidth should be greater than or equal to size divided by TF. You know the size of the frame, you know TF, here 4.815, right? So size is 1000 bits, TF is 4.815, so the answer is 207 kbps. So on the second link, if you use the data rate 207 kbps, then there should not be any problem of buffer overflowing or flooding. Why? Because the first link uses only 100 kbps. On the first link, the transmission happens at the rate of 100 kbps. So though on the first link we use sliding window, because now we use a larger bandwidth, 207 on the second one, the number of frames sent or received on the first link would be less than or equal to the number of frames that can be sent on the second link. So that's the answer. Let me stop here. Any doubt? So before we dismiss today, the quiz will be on 1st March. Okay, later I will 1 to 2 p.m. Wednesday. So Wednesday we will have quiz 1 to 2 p.m. So I want to see all students. So this room is not adequate. So the venue will be LT11. Of course, later I will send the announcement. The test is going to be conducted in LT11. I think it's next to library or somewhere, this side. I also am yet to see that. Okay. March 1st, Wednesday, same class period. Okay. That means week 7. You have break. Prepare yourself when you have time. Of course, I cannot force you because it's a break. If you want to enjoy, you can enjoy. If you want to spend some time, you can read the topics. Okay. Then Monday, Prof. Mehul Mutani will teach because I will complete next week. So Monday, week 7, there will be lecture by this other lecturer, Professor Mutani. Wednesday, I will conduct the test. Is that okay? The test is not here. It's going to be in LT 11. And the topics is notes 1 to 5 only. Lecture note 6 is not included. I have not yet taught lecture note 6. But lecture note 6 on wireless net will be there for the final exam. Okay? For the test, it is 1 to 5. It's MCQ. There will be 15 questions. So all kind of, you look at the sample questions, all kind of multiple choice questions would be there. Some would require numerical solution. You have to do some calculation. Okay? Some would be, okay, pick up the false statement, right? Or match, okay, choose the incorrectly matched pair, something like this. Okay? So I'll be testing the conceptual understanding. You should know the topics, and also some questions will be on the numerical problems. You can bring the calculator to do that. But it's a strictly closed book. No help sheet is required. No help sheet is allowed. No book is allowed. Nothing is allowed. Okay? Is it okay? And of course, for some question, you may have to spend time. You know the calculation, but still I give you 1 mark. For some questions, you may not need to spend much time because you know the answer within seconds. You can choose. If you don't know the answer, even if you try 1 minute, 2 minutes, 3 minutes, if I ask what is a false statement, which of the following statements is false, no point in spending too much time, right? But still I give equal marks for everything. Why? Sometimes using the formula blindly, anybody can do, okay? But you should have a good understanding of the lecture topics. That's also important. Another reason is MCQ has pros and cons, okay? Sometimes without knowing the answer, you get mark for that. Randomly you choose something, or you think, okay, but somehow you chose the correct answer. You don't know how you chose the correct answer, but still you get 1 mark. Some questions you tried your best, okay, you got an answer, may not be correct, but unfortunately that false, incorrect answer is also there as one of the options. Then you lose, okay? So you should not be disappointed, oh, I spent 10 minutes time, 5 minutes time, I got it wrong. You are losing only 1 mark. Don't worry, okay? Maybe you might have gained by guessing some questions. So sometimes you lose even if you work hard. But overall, generally students do well. So you read through the lecture notes, tutorial problems, sample questions, and other questions. And if possible, read the books. I always tell the students to read book. Even I also read books whenever I find time. Okay. Of course, to teach this, I don't need. I'm teaching this for several years. Okay. So, but better you read books for better understanding. Or if you have any doubts, okay, feel free to send it to me. But as I said, I think I said before, if you have any doubts, better you take a screenshot of that. That's easy. Okay. Because sometimes students ask lecture notes 5, slide number 52 or something. So if you take a screenshot, I can answer it. Even if I'm traveling in the bus, I can answer it, right? Otherwise, I have to go to office or house, open my computer. Is that fine? And before the test, I will conduct one special session, maybe on Zoom. Okay. I'll go through the sample question answers. And also, if you have doubts, okay, based on your reading, if you have any doubts on the topics, okay, so we can discuss it. So there will be a special consultation session before the test. Let me stop here. See you on Monday. And one more thing, attendance for the test is compulsory, not like this, no makeup test. I need to be fair to everybody who is taking the test, right? So I want to evaluate everybody on the same question paper. So please attend the test without any fail, unless you have very emergency reason, like hospitalized or something. Not for small reasons. Don't ask for makeup test. Okay? No negative marks.